Good day, everybody. I am Signe Kjellstrup. I'm going to lecture to you on non-equilibrium thermodynamics for engineers. It is about this book we are going to talk. This book has the title Irreversible Thermodynamics for Engineers, and the two ways of naming the field are equivalent. So, of course, now at the outset of the course, you would like to know why you should study this field. And I'm going to give you 5 good reasons to invest work in this field. Let's look at the first one. I assume that you are familiar with the second law of thermodynamics, the way it is taught in basic courses. Then you know that the entropy change of the surroundings, denoted by the 0, plus the entropy change of the system is always larger than 0. It can be 0, then the process is reversible. So this gives a description of a preferred change from one state to the other. It's not very specific, so we would like to have time as a variable. And this is the first reason for including or studying irreversible thermodynamics. It introduces time as a variable. We do that in this way, grossly speaking. You can take the entropy change of the system and the surroundings, the right-hand side of this equation, and look at the average of that change over some time period, and then you get the left-hand side here. So that's an identity. Now, the time rate of change, the average over a small time of the entropy change of the system and surroundings, that can be formulated also locally by the function sigma in this equation. For simplicity, I have chosen transport only in the x direction. Of course, in nature, transport occurs in all directions, but we are looking at the principles here, and it's enough to study one direction. So, in a very small, in a volume element along the x-axis, here we have the entropy change per unit of time, and if we integrate over the x-axis over the whole length of the system and multiply by the cross-sectional area, we get again the entropy production of the whole system as you learned about it in the second law. However, we get something more, because now this theory, non-equilibrium thermodynamics, comes in and says that the local entropy production is a product sum of all fluxes, J, and forces, X, in the system. Don't worry about the fluxes and forces yet. The course is about defining them. Now I give you the reason for why you should look into this. You see that we get a formulation of the second law of thermodynamics that includes time. Now that can be useful. What other reasons are there? It's not only the entropy production that's important. The whole entropy balance is important. Now, entropy is a property that is not conserved. Think about the mass balance, the mass density will be the flux, the change in the mass density will be the variation in the mass flux across a volume element. That is not so for the entropy. If we have the volume element here along the x-axis, you see the cross-sectional area here, omega I called it, so this is a volume element. Let's look at the changes in that. The change in the entropy density here per unit of time is minus the divergence of the entropy flux through the element. So if the flux in is different from the flux out, there will be an accumulation in the entropy in the volume element. That's the first term on the right-hand side. But we can also have a source of entropy, and that's the entropy production, the last term in this equation. It is this that is given in terms of the fluxes and forces and the product of all such flux-force pairs. The entropy source strength, or the entropy production, that is. Now, very often we are in a situation where there are no time rate of changes, then there is no accumulation of entropy in a volume element. Then simply the entropy production for the whole system, like we saw it on the previous slide, is given by the entropy flow out minus the entropy flow in. The flows or the fluxes are given per square meter. So if we multiply by the cross-sectional area again, we get the whole entropy produced in the whole box we are looking at. So we have the entropy balance as a balance equation with more detailed information about the entropy production, and that makes an additional equation that you can use together with what you have used already. Maybe you have used the mass balance, you have used the energy balance and the momentum balance to calculate your system so far, I think. And now I'm saying that we have an extra opportunity. We can use the entropy balance also to solve our unknowns or to check on our system. Second reason that was, what more is there? Now we come to the main postulate of non-equilibrium thermodynamics. Each flux, here you see an example of a heat flux, a mass flux, and the electric current density. Each of these fluxes are given as functions not only of one force, but of three forces. The heat flux is given as a function of the temperature gradient, as a function of the gradient in chemical potential, and it is also proportional to an electric force. Now, these forces have a particular form, and we are going to derive them, so don't worry about them yet. What is now interesting is to look at these three equations and compare them to what you may be familiar with already, namely the empirical laws of Fourier, Fick, and Ohm. These empirical laws are valid for many systems, and they are rather simple. They say, for instance, if we take Fourier's law, that heat flux through a system follows a falling temperature variation. You have a positive heat flux in the direction of a falling temperature profile. That is, the heat flux is proportional to minus the gradient in the temperature. And the proportionality constant is the thermal conductivity. Similarly, very analogously, the mass flux is proportional to the concentration gradient, and the proportionality constant is a diffusion constant, the d. And Ohm's law tells essentially the same. The electric current density is proportional to the electric gradient, and the proportionality coefficient is the electric conductivity. That was the start of science. That was discovered in the 18th century. But nature and industry is more complicated, and with the precision that is needed nowadays, we need non-equilibrium thermodynamics. Non-equilibrium thermodynamics gives more complicated expressions for the rate laws. We can recognize the simple rate laws if we look here at the current density. You see that the gradient in the electric potential is here. So the product of L55 over 1 over the temperature is in fact identified as the electric conductivity. And here, in the heat flux equation, you have the derivative of 1 over t is d over t squared, dt over t squared, with a minus in front. So LQQ over t squared can be identified with the thermal conductivity. You can make a similar identification with L mu mu and the diffusion coefficient. It's more complicated, however. But I'm only now saying that the empirical simple laws are covered by the diagonal elements in this complicated matrix. So non-equilibrium thermodynamics gives you more transport coefficients. And if you look at the matrix, it seems like there are 1, 2, 3, 4, 5, 6 new coefficients in addition to the old ones. And that's a pity, because that means that more information, more experiments are needed, maybe. Well, the founder of non-equilibrium thermodynamics, Onsager, he proved that life is not so complicated. This matrix is in fact symmetric. He showed that the coefficients were pairwise identical. This one was equal to this one. The LQ phi was equal to L phi q. And he proved also that L phi mu was equal to L mu phi. He used microscopic reversibility. He used the fact that molecules obey Newton's laws, and then he used the assumptions of linear flux force relations, and he was able to derive these relations. And that simplifies our system. So, more detailed transport laws we have, and we have the safety that they are derived directly from the second law. Good to know that you work in agreement with the second law, isn't it? But there are more reasons. Coupling, you may think that these extra coefficients, the coupling coefficients, are not important. After all, they could be small. And if we are on the 10% level, why bother? We capture most of them, the effect with the simple laws we have, do we? That's a question to ask. Is coupling important? Well, I have taken along a picture here from the polymer electrolyte fuel cell to explain you why it is important. The polymer electrolyte fuel cell consists of these green pictured here polymers which are charged. You see they have negative sites on the picture. These charges are compensated by protons, the little white dots with a plus here. But the protons don't go alone across the membrane from the hydrogen electrode where they are produced to the oxygen electrode where they should react and form water. They go together with water. So we have pictured every little white dot here with a red oxygen and two blue another protons attached. Water goes along with the proton. And they meet the oxygen on the platinum catalysts that you see here. And if there are enough of them that you see here, they will react and form the intermediate peroxide. So immediately you are in a situation where mass transport is following charge transport. And the charge transport is creating the electric work in the fuel cell. So you see that the coupling, not only of water to protons, but also the connection between oxygen and the proton, they are also uniquely coupled, gives you something important. It gives you work. And along with this mass transport, you can also have heat transport. The chemical reaction at the catalytic site involves also heat. All these transport phenomena are interlinked. They are coupled, we say, in non-equilibrium thermodynamics. And they even give you the essence of the system you are working with, like in this example, the fuel cell that I have taken. Similar things occur in batteries and osmosis plants. We will go through them through the course as we go along. So that's important. The important point of the coupling coefficient. It will tell us whether we can use the system to produce work. And even if it is small, it may still be important, like in the thermocouple. There is a small coupling between heat and charge transport, but it is that small coupling that makes the thermocouple work. It works because a temperature difference and a heat flux will trigger an electric potential difference. So it's very good reasons to go to a more sophisticated level in your transport equations. Here is a very different reason for why you should study irreversible thermodynamics. When you have a systematic theory, like you get from this theory, you can use that to your advantage to design experiments. Experiments can be well defined, we say, from the flux equations. Here you see again the flux equations that I used as an example in the previous slides. And let's look at the ohmic conductivity. We were speaking about the ohmic conductivity, this coefficient. Now you may say that the ohmic conductivity is the ohmic conductivity. Please look up in books how that is measured, because you see that the ratio of the current density over the electric potential that I write on this line, in order to have L phi phi only, I need to make sure that the temperature in my system is constant, as well as the concentration or the chemical potential must also be constant throughout the system. So the ohmic electric conductivity is measured, or it is defined for a homogeneous conductor. That says, if you make any other condition than these, you get a different answer. You can have the same ratio, the ratio of the electric current density and the electric potential gradient. But if you have different conditions, like here in the stationary state, you can have no mass flux and no heat flux. Doesn't say that the temperature difference is zero. It can be balanced by another force according to these differences. You see here, the other terms can, this mass flux here, if that is zero, it means that there are other terms that compensate. We know that this is not zero in the experiment, the last one. So this term here must be balanced by the two other terms. And then you realize a situation with zero mass flux. And the answer is very different from the other answer. The experiments have been defined in a different way. It's been well defined. So that's an advantage for an experimentalist to have a systematic theory. And the same argument applies to many transport of coefficients, of course. Yeah, that was reason number 4, I think. Let's look at the last reason. We will get a better handle on the lost work. The lost work is already calculated to a large extent in a field called exergy analysis, which you may be familiar to. Let's go through exergy analysis, which shows the relation between lost work and the entropy production of the system. This development follows the famous Denby from the 50s. In exergy analysis, you have the advantage that you could look at a big process, a whole factory. Many units are in the factory. And you can take the energy change of the process by taking the difference in energy out and into the factory. That's my delta U now. So that energy difference by processing the materials, that is according to the first law, here, the first law, equal to the heat input to the process minus the work done against the surroundings, which has a pressure of P0, and then there is extra work needed from the electricity net, maybe. So we are, of course, interested in this extra work. How much work do we need to supply to the process? Well, we reshuffle the equation a little bit here, because we replace the heat delivered to the process by the heat delivered to the surroundings. So Q is equal to minus Q0. Then we have again the second law in equilibrium thermodynamics. And the way we now write it for the whole system in non-equilibrium thermodynamics to make the link to that field. And you can see that I can now replace delta S0 in this equation by Q0 over T0 of the environment, because the environment has a constant temperature. So that's the easy replacement I can do. And then I introduce the replacement for Q0 in the first law by this equation, and I get the expression for work that I'm interested in. And you see immediately the important thing. We have a term here which is multiplied by the temperature of the surroundings, and it's the entropy production of the system. And then we have other terms which do not depend on anything else but the input and the output for the system. These last terms, that is a state function. You know that the entropy production could be zero if the process is reversible. In that case, we speak about the smallest work needed to accomplish the process. That's the ideal work. But the entropy production is never really zero. It's always something. There is always some loss. You can think of it as a frictional loss, really, to drive the factory. So, in reality, we need more work than the ideal one. So you could speak about something, this difference between the real work and the ideal work, that you can consider also as lost work. Now, it's lost compared to the ideal reference, but there must necessarily be losses because we want to accomplish things in a given time. But we, as engineers, want to make that loss small. So, in order to make it small, we first have to know about it. So we would like to have this knowledge on the entropy production, and we can get it from equilibrium thermodynamics data, like we know here. But we can also get it from the time-dependent variables of the process. And that gives you an extra handle on the lost work and maybe helps you to understand it. Let's look a little bit more on that issue. So here is again the same expression for the lost work that we had in the previous slide. So if I now know that in a chemical reactor I have certain boundary conditions, I have temperature, pressure and composition in, then I will have some different temperature, pressure and composition out. The reactor has a length L here and a diameter D. So could I link the entropy production to what is happening inside? That would be an advantage, because then maybe I could control that later. Yes, I can, because we have seen that I get the total entropy production by integrating over the local entropy production. In this case, the transport coordinate is the z coordinate. Here are contributions to the entropy production from the flux of the chemical reaction, and the driving force for the chemical reaction gives energy of the reaction over T with a minus sign. The rho is some density if you give the reaction rate per kilo of catalyst. This gives the catalyst density. And the second term in the reactor comes from temperature leakage across the wall of the temperature of the reactor and heat flux in this direction. And the pi and the d are geometrical variables that take care of this being the transport direction for this term. And the third term here gives you the friction of the flow, because v is the velocity of the flow and dp dz is the gradient in pressure along the reactor. So you see, don't worry so much about the symbols, we come to them later, but overall the main message at this stage is now only that I can use very detailed and local information about what is going on here, 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 and I can integrate out and get the total lost work. And I can understand why the lost work is the way it is, because I can go back and find out where were the contributions. And also, so this gives a possibility to calculate the lost work, but also, like I said, we can calculate the entropy production from the entropy balance. So here is the same reactor, and rather than calculating the contributions everywhere along, like I did explain in the previous slide, I can just take the whole box or the whole reactor like this and say that the total entropy production is what comes out at the end, what goes minus what comes in here. These are now the entropy flows. And if there is heat flow across the boundary, I also need to account for this outflow of entropy, JQ over TA. TA is the temperature of the surroundings. That gives you the entropy flow to the surroundings. And I must integrate also that. So that's a different calculation. But it's wonderful to have two ways of calculating the same thing, because that makes you absolutely sure that you have done it correctly, and it gives a handle on your system as well. So you see, there are many reasons why this theory can help you to be a better engineer in practice, and I think it's good to summarize all of them in the end. You should study non-equilibrium thermodynamics because you will obtain a more specific formulation of the second law than you have used in equilibrium thermodynamics. You will include the time as a variable and rates. You will have an entropy balance that you could solve in addition to the other balances that you know for a system. And that may be an opportunity to control your system better. It's very comforting to know that your transport equations derive from the second law. Then you know that your system obeys the second law. You have not created any inconsistencies or contradictions in your model. That's also a good reason to study this course. And it's helpful to have a systematic framework when you define experiments. It's always going from theory to experiments. There's always also a path back. Once you have experiments, you like to understand them, and then you go back to the theory. Now, if the experiments were not designed according to the theory, it's not so simple to go back. So experiments poses challenges to theory, and theory can help design experiments. The two should go hand in hand, really. And then, in our time, with the lack of resources, especially of energy, you should know what the lost work of your system is. And you should also know how to make it smaller. But in order to make it smaller, you should understand why it is the way it is. And I think we can get a better understanding of the lost work from non-equilibrium thermodynamics, because it connects the rates and the underlying molecular causes for these rates to the overall performance of your plant. And this transition from the molecules to the plant, that's the theory can help you to make. So, not only the lost work is important to understand, it's also important to understand the actual work. And we will return to those issues, be sure. Thank you.